What would happen if you fell into a black hole? Would you be crushed instantly, stretched into infinity, or perhaps witness the entire future of the universe in your final moments? Somewhere in the dark between the stars, there are places where gravity has won completely, places where light itself cannot escape, places where space and time twist into shapes that no human mind was ever meant to hold. Tonight, astronaut, we take that journey together, not as a story of fear, but as a slow drift into the deepest mystery in physics. We will fall carefully, patiently, into the darkest object the universe can create. If you find peace in these cosmic journeys, consider subscribing. We will be here every night, exploring the universe together, one quiet wonder at a time. Welcome aboard, astronaut. Tonight, we drift through the cosmos. Close your eyes if you wish. Let the weight of the day fall away. Tonight, we leave Earth behind. We leave the sun behind. We leave every familiar orbit, every familiar sky, and travel toward a point where reality itself begins to fail. A black hole is not merely an object in space, it is a boundary, a threshold, a place where the known laws of physics stretch until they break. For more than a century, scientists have asked the same question that now guides our journey. What would you see if you fell in? What would you feel? And what would the universe reveal in those final moments of consciousness? This is a thought experiment. No ship can carry us there. No body could survive the voyage, but the mind can travel where matter cannot. And so we go. There is no need to rush. In the vastness of space, patience is the only virtue that matters. We will move slowly. We will pause. We will look carefully at every stage of the fall, from the first distant approach to the crossing of the event horizon, to the strange fate that waits at the center. Let us begin our descent. Before we fall, we must understand what awaits us. A black hole is not truly a hole at all. It is not an empty tunnel through space. It is an object, a remnant, the densest concentration of mass that nature allows. In many ways, it is the ultimate presence, a place where matter has been compressed so completely that it warps the fabric of reality around it. Every object with mass bends space and time. The Earth bends space-time gently, enough to hold the moon in orbit. The sun bends it more strongly, enough to hold the planets. These are soft curves in the cosmic fabric, quiet distortions you would never notice with the naked eye. A black hole bends space-time so severely that it creates a pit from which nothing can climb out. Not rockets, not light, not information of any kind. The boundary of this pit is called the event horizon. It is not a wall you can touch. It is not a surface you can stand on. It is a mathematical boundary, a point of no return. Once you cross it, your future points only inward. Every path, every possible tomorrow leads toward the center. At that center lies the singularity, a region where our equations produce infinities, where density becomes unimaginable, where our understanding of reality reaches its absolute limit. This is the destination of our fall, astronaut. But we will not rush toward it. First, we must learn how such a thing is born. Picture a star, perhaps 20 times the mass of our sun. For millions of years, it burns brilliantly in the dark, deep in its core. Hydrogen fuses into helium. Helium fuses into carbon. carbon into oxygen, oxygen into silicon, and onward, climbing the ladder of the periodic table, releasing the energy that holds the star against the pull of its own gravity. A star is a balance, outward pressure from fusion, inward pull from mass. As long as that balance holds, the star lives. But this process cannot continue forever. Eventually, the star creates iron in its core, and iron is the end of the road. Fusion iron does not release energy. It absorbs it. The furnace that once held the star aloft begins to fail. In that moment, the star loses its ancient battle against gravity. The core collapses. In less than a second, matter that once occupied a space the size of Earth is compressed into a sphere only a few miles across. The outer layers, having nothing left to support them, come crashing down. They strike the dense core and rebound in a supernova explosion so bright it can outshine an entire galaxy. What remains depends on the mass of that core. If the remnant is light enough, it may become a neutron star, a city-sized sphere of matter so dense that a teaspoon of it would weigh billions of tons. But if the core is massive enough, gravity continues its work. The matter is compressed further and further until no known force can resist. This final collapse creates a black hole. The star that once lit the night for millions of years becomes a region of darkness so complete that even light cannot leave. Not every black hole forms this way. Some grow by merging with other black holes. Some may have formed in the early universe from the direct collapse of enormous gas clouds. Some sit at the centers of galaxies and have been feeding for billions of years. But the principle remains the same. Enough mass in a small enough space, and space-time itself folds shut. Black holes come in different sizes, and size changes everything about the fall. The smallest common black holes are stellar black holes, formed from collapsed stars. They might be only 10 to 20 miles across, small enough, in principle, to fit inside a city. Yet they contain the mass of several suns. Near such an object, the gravitational gradient is extreme. The difference in pull between your head and your feet becomes lethal long before you reach the event horizon. A fall into a stellar black hole would be brief, violent, and finished before you ever cross the point of no return. Then there are intermediate black holes, hundreds or thousands of times the mass of our sun. We believe they form when stellar black holes merge, or through other processes we do not yet fully understand. They are rarer in our observations, quieter in the data, still partly hidden from us. And finally, there are the monsters. Supermassive black holes, millions, even billions of times the mass of our sun. These giants lurk at the centers of galaxies. Our own Milky Way harbors one called Sagittarius, a star. It contains the mass of about 4 million suns, compressed into a region smaller than our solar system. Other galaxies host black holes far larger still, some containing billions of solar masses, dark engines at the heart of cosmic cities. For our journey tonight, we choose a supermassive black hole. Why? Because a larger black hole, paradoxically, offers a gentler experience. The gravitational forces change more gradually across the distance of your body. You would have time to observe, time to experience, time to witness the strange phenomena that await. A stellar black hole would tear you apart almost at once. A supermassive black hole might give you minutes, perhaps longer, of conscious experience after crossing the event horizon. So let us approach one now, slowly, from a safe distance in the mind, and watch the universe change as we draw near. As you drift closer, the first thing you notice is the darkness. A black hole does not glow like a star. It does not reflect light like a planet. It is simply an absence, a void in the star field, a place where the universe seems to end. From far away, it might look like nothing at all, just a quiet hole in the pattern of stars. But look more carefully, and the sky begins to lie. The light from stars behind the black hole is bent, warped, curved around the invisible mass. Stars that should be hidden appear beside it, their light following the curvature of space-time like water flowing around a stone. Multiple images of the same star may shimmer at the edge of the darkness. Circles of light form where none should exist. This is gravitational lensing. Einstein predicted it more than a century ago. Space itself is curved by mass, and light has no choice but to follow that curve. You are no longer looking at ordinary space, astronaut. You are looking at geometry under pressure. And still, you fall closer. The stars near the edge of the black hole seem to crowd together. The darkness grows, not because more light is missing, but because more of the sky is being claimed by the warped region around the event horizon. The universe is rearranging itself for your eyes, preparing you for a boundary that has no surface and no warning sign. Look again, and you may see something brilliant around the darkness, around many black holes. There is a ring of light. This is the accretion disk, gas and dust captured by the black hole's gravity, spiraling inward like water circling a drain. This material does not fall straight in. Angular momentum forces it to swirl. Friction between layers moving at different speeds heats the gas to millions, even hundreds of millions of degrees. The inner disk can glow with X-rays. The outer regions shine in ultraviolet and visible light. In some systems, the accretion disk outshines entire galaxies, releasing more energy than 1 trillion ordinary stars. This is one of the great ironies of black holes. They are famous for darkness, yet the matter falling toward them can become the brightest light in the cosmos. Magnetic fields twist through the disk. Jets of plasma may launch from the poles, racing outward at nearly the speed of light, carrying energy across thousands of light years. The black hole itself emits nothing from within the horizon, but the environment around it can be furious with radiation and motion. For our fall tonight, imagine a quieter, supermassive black hole. Not a raging quasar, not a cosmic engine in full hunger, just enough of a disk to mark the way. A faint, glowing ring, a last lantern before the dark. You pass above it carefully in the mind. The temperatures here would destroy any real body. The radiation would be lethal. But you are an observer made of thought, and thought can endure what flesh cannot. The disk is the last familiar kind of light you will see. Beyond it, the rules change. Closer still, there is a region where light itself can orbit. This is called the photon sphere, for a non-spinning black hole. It lies outside the event horizon at 1.5 times the horizon radius. Here, photons can circle the black hole again and again, trapped in unstable orbits. before eventually spiraling inward or escaping to infinity. If you could place a beam of light carefully at this radius, that light would loop the black hole like a ghostly ring. In practice, those orbits are unstable. A tiny disturbance sends the photon away or down, but the idea remains: light can be held in orbit by gravity alone. From the outside, this region helps create the bright ring seen in black hole images. The Event Horizon Telescope has captured such rings around the black hole in the galaxy Messier 87 and around Sagittarius A star in our own Milky Way. What we see is not the black hole itself. We see the shadow it casts against glowing matter, and the light bent into a ring by extreme gravity. You are now near that shadow, astronaut. The photon sphere is a warning written in light. Inside it, escape becomes harder. Farther in, escape becomes impossible. And just beyond this luminous boundary, the event horizon waits. The event horizon is the most significant boundary in the universe, and yet you cannot touch it. There is no wall, no membrane, no flash of arrival, no sign that says point of no return. It is a distance, a radius, a condition of spacetime. It is the place where the escape velocity equals the speed of light. Inside this boundary, nothing can climb back out. Not matter, not light, not a message, not a memory sent home. For a stellar black hole, the event horizon may be only miles across. For a supermassive black hole, it may span tens of millions of miles, larger than the orbit of entire planets. Size does not change the meaning of the boundary. It only changes how gently or violently you meet it. As you approach, an outside observer would see something strange happen to you. Your clock would appear to slow. Your movements would grow sluggish. Your radio signals would stretch into longer and longer wavelengths, reddening, fading. To them, you never quite cross. You slow and slow and slow until your image freezes near the edge, a ghost preserved in time, growing dimmer over ages. But this is only their view. From your perspective, time still feels normal. Your heart still beats. Your thoughts still move at their usual pace. You cross the event horizon in finite time. There is no bump, no special sensation at the exact boundary. Space around you may still seem ordinary in the first moments. You have simply become disconnected from the cosmos. Any light you send outward now curves back. Any call for help ends at the horizon. The universe outside can no longer receive you. You can still exist. You can still fall. But you can no longer report what you find. This is the true meaning of the event horizon. Not a wall of death, but a one-way membrane in space-time. A place where communication ends, even if consciousness briefly continues. Let us cross it, astronaut. No ceremony, no thunder, only the quiet realization that every future path now points inward. Outside a black hole, you can move left or right, forward or back, up or down. Time alone forces you forward. Inside the event horizon, something deeper changes. In the language of relativity, the radial direction becomes time-like. Just as you cannot avoid tomorrow in ordinary life, you cannot avoid the center of the black hole once you are inside. The singularity is no longer a place you might miss. It is a moment in your future. This is difficult to hold in the mind. It challenges the ordinary meaning of space, but the mathematics is clear enough. After the horizon, all roads lead to the same destination, and yet, for a supermassive black hole, the crossing itself can be strangely calm. Because the horizon is so far from the center, the tidal forces at the boundary may still be gentle. You could cross intact, body whole, mind aware, still able to look around, still able to wonder, what would you see if you looked back? The outside universe would begin to change. Light falling after you would be distorted. The sky might compress into a bright region above, while darkness claims more and more of your view. Time outside would seem to race. The connection to the world you left would thin, then vanish. You are inside now. There is no going home. Time near a black hole does not behave like time on Earth. According to general relativity, gravity slows time. The stronger the gravitational field, the slower clocks tick compared with clocks far away. This is not science fiction. It has been measured on Earth. Clocks on satellites run slightly faster than clocks on the ground. Time passes a little more slowly at the surface of the sun than it does in deep space, near a black hole. The effect becomes extreme. To a distant observer, your fall toward the horizon seems to freeze. To you, the fall continues. Both descriptions are valid. They are two coordinate stories of one space-time event. The asymmetry between these perspectives is one of the strangest facts in physics. Two observers can disagree about the duration of the same journey, and both can be right within their frames. Inside, another strangeness grows. As you fall deeper, light from the outside universe is blue shifted. It gains energy as it descends the gravitational well. Stars that once looked red may shine blue. Blue light may shift toward ultraviolet, ultraviolet toward X-rays. The sky behind you becomes not only distorted, but dangerous with energetic light. Some popular accounts say a falling person might see the entire future of the universe flash by, stars dying, galaxies fading, the heat death of everything compressed into a final instant. The poetry of that idea is beautiful. The physics is less kind. Long before such a cosmic history could be calmly observed, the blue-shifted radiation would become lethal. The light of the outside world would not arrive as a gentle film of the future. It would arrive as a storm of energy. Still, the deeper truth remains. Near a black hole, time is not a universal river flowing the same for all. It is local. It is shaped by gravity. It can stretch, slow, and split experience into incompatible views of reality. You are living inside that split now, astronaut. Outside, ages may seem to pass. Inside, your own clock still measures only the short remaining path to the center. Now the journey becomes more personal. As you fall deeper, you begin to notice a gentle tugging, a feeling of being stretched. At first it is subtle, almost polite. Then it grows. This is the beginning of spaghettification. Gravity follows an inverse square law. The closer you are to a massive object, the stronger the pull. That also means different parts of your body experience different forces. Your feet, being closer to the singularity, are pulled harder than your head. At first, the difference might feel like nothing more than a slight extra weight. Then the stretch becomes clear. Your spine elongates, your arms drift. You grow taller and thinner, moment by moment. At the same time, you feel compression from the sides. Space-time curves inward toward the center. Left and right are pressed together, while up and down are pulled apart, stretched vertically, compressed horizontally. This is tidal force. On Earth, tidal forces from the moon raise the oceans. Inside a black hole, tidal forces unmake bodies. For a stellar black hole, this process can begin far outside the event horizon. You would be torn into a stream of matter before you ever cross the point of no return. For a supermassive black hole, the horizon may be crossed while you are still whole. The worst stretching waits deeper in, closer to the singularity, where the gradient of gravity rises without mercy. Eventually, no structure can hold. Bones separate. Tissue fails. Atoms are drawn into long filaments. You become, in the cold language of physics, a stream of particles on inevitable paths. Scientists chose a strangely ordinary word for this fate: spaghettification, as if the cosmos itself had a dark sense of humor. It is not a gentle end, but it is a precise one, the same law that shapes planetary tides, written at a scale where flesh cannot remain flesh, and still, for a time, before the final extreme, a traveler into a giant black hole might remain aware, might still think, might still understand what is happening. That window of awareness is why we chose a supermassive black hole for this journey, not because the ending is kinder, but because the path to the ending is longer, and more can be witnessed along the way. Inside the event horizon, the darkness is absolute in a way ordinary space never is. Between the stars, there is still starlight, still the cosmic microwave background, still faint photons wandering from distant ages. Inside a black hole, once you are deep enough, no light from the outside universe can help you. You fall through a void more complete than the gaps between galaxies, a darkness unbroken by any ordinary lamp of the cosmos. And yet, the interior is not empty of structure. Space-time still has geometry. Paths still exist. The singularity still waits as a future event. Some models describe strange optical effects, light looping, images shearing, directions losing their familiar meaning. Whether a real falling observer would consciously see such things is uncertain. Radiation, heat, and tidal stress may erase calm perception long before elegant visions appear. What is certain is the loss of choice. Outside, you could, in principle, turn a ship around, fire engines, change course. Inside, the engines do not matter in the old way. The destination is fixed. The singularity is not a room you enter by bad navigation. It is a time you arrive at as surely as morning follows night. This is why black holes unsettle us so deeply. They do not merely threaten death, they rearrange the meaning of escape. They take the open map of space and fold it into a one-way corridor of time. You are in that corridor now. There is still a little while left in the fall. Use it in this imagined journey to look toward the greatest mystery of all. At the center lies the singularity. According to classical general relativity, it is a point of infinite density. All the mass of the black hole compressed into zero volume, infinite curvature, a place where the known equations stop making sense. But most physicists do not believe infinity is the final answer. Infinity in an equation is often a confession. It means the theory has been pushed beyond its valid range. General relativity is extraordinarily successful, yet it is not complete. It does not include quantum mechanics. Near the singularity, both gravity and quantum effects should matter, and we do not yet have a tested theory that unites them. So, what is really there? We do not know. String theory offers possibilities. Loop quantum gravity offers others. Some ideas replace the point singularity with a highly curved but finite region. Some suggest a bounce. Some imagine a gateway into another region of space-time. Some propose that a black hole birth might be connected in exotic solutions to a white hole or even a new expanding universe. These are speculations. Beautiful, disciplined, mathematical speculations, but still speculations. In realistic collapse, with matter falling in and imperfections in symmetry, the interior is likely chaotic and severe. The romantic image of a clean tunnel to another cosmos is probably too simple. The true singularity, or the quantum region that replaces it, may be the most hostile and alien environment nature can create. What we can say is this: as you approach, tidal forces grow without limit. In the classical picture, every structure is destroyed. You are not merely killed, you are unmade. Matter, energy, and the arrangement of information that once was you join the black hole's hidden interior in a form we cannot yet describe from the outside. In a sense, everything that falls in becomes part of the black hole's mass and history. Stars, gas, dust, light, planets, and in our thought experiment, you, the singularity, is where the story of your fall ends as a person and continues only as physics we do not fully understand. And yet, even black holes are not eternal. In one of the great insights of the 20th century, Stephen Hawking showed that black holes slowly evaporate. The process is called Hawking radiation. According to quantum mechanics, empty space is not truly empty. It seethes with temporary fluctuations. Pairs of particles and antiparticles appear for brief moments and vanish again. Near an event horizon, these fluctuations can be separated by the boundary itself. One excitation falls in, another escapes to infinity. The escaping radiation carries energy away. To conserve the books of nature, the black hole loses mass. Particle by particle, over immense ages, it shrinks. For a stellar black hole, complete evaporation would take an unimaginably long time, on the order of 10 to the power of 67 years. Far longer than the current age of the universe. For a supermassive black hole, the time scale grows even more extreme, perhaps 10 to the power of 100 years or more. During those eons, the universe will change beyond recognition. Stars will die, galaxies will drift and fade. The night will grow colder and emptier, and still, the black holes will remain, slowly leaking, slowly fading, the last major structures in a darkening cosmos. In the final stage, evaporation accelerates. A smaller black hole is hotter, it radiates faster. In its last moments, it releases a final burst of energy, and then it is gone. All that mass, all that swallowed light and matter, converted into radiation, scattered into the thin future of the universe. If you fell in long before that end, your matter would not remain forever as a permanent prison. In the far future, even that prison dissolves. The black hole that held you also dies. But a deeper question remains. What happens to information? Quantum mechanics suggests that information about a physical system is never truly destroyed. In principle, the past leaves records in the present. Evolution is reversible at the fundamental level. The universe keeps accounts. Black holes seem to threaten that principle. They swallow detailed information about everything that falls in, and later appear to return only featureless Hawking radiation. If the radiation is truly thermal and random, the information seems lost. If information is lost, quantum theory faces a crisis. This is the black hole information paradox, one of the deepest unsolved problems in modern physics. Many ideas have been proposed. Perhaps information is encoded in subtle correlations within Hawking radiation. Perhaps it is stored on the event horizon in a holographic way. Perhaps black hole interiors and exteriors are linked by principles we are only beginning to name. Perhaps new physics appears near the horizon itself. We do not yet know the answer. There is a quiet irony here, astronaut. The object that seems to erase everything may force us to learn how the universe remembers. By studying the darkest places, we may discover the deepest rules of information, gravity, and reality. If a falling observer could somehow understand the interior completely, they might glimpse the resolution, but no signal from inside can confirm it to those who remain outside. The paradox is not only a scientific puzzle, it is a reminder of the horizon's silence. Before we rise from this journey, let us briefly imagine the other path, the fall into a stellar black hole. You approach a dark object only miles across, the remnant of a dead star. Long before the event horizon, the tidal forces become monstrous. Your body is stretched along the line toward the center. The difference in gravity between head and feet grows unbearable. Spaghettification begins in open space under the cold light of distant stars. There was little time for philosophy, little time for watching the sky transform. The destruction is earlier, sharper, more immediate. You may never cross the horizon as a whole being. You may arrive only as a stream of matter already undone. This contrast is important. Not all black holes offer the same story. Mass changes the timeline of doom. A giant black hole can hide its worst violence deep inside. A small black hole announces that violence early with raw tidal force. Popular culture often treats black holes as one single nightmare. Nature is more precise. There are many nightmares scaled by mass, spin, and environment. Our choice of a supermassive black hole was not to make the tail safer. It was to make the tail longer, so that more of the physics could be seen before the end. There is still another layer. Real black holes often rotate. When a star collapses, it usually carries spin. When black holes merge, they can leave a spinning remnant. A rotating black hole is described by the Kerr solution, and it is richer than the simple non-spinning picture. Around a spinning black hole, space itself can be dragged. This is frame dragging. Near the hole, free-falling matter is forced to swirl with the rotation of spacetime. There is a region called the ergosphere, outside the event horizon, where it becomes impossible to remain still relative to distant stars. You must rotate with the vortex of geometry. Spin also changes the shape of the horizon and the possible paths of light. It changes how close stable orbits can exist. It changes the efficiency with which an accretion disk can radiate energy. In some theoretical models, spin even opens more exotic interior structures, though nature may destroy the cleanest versions of those interiors through instability and in falling matter. If you fell toward a spinning supermassive black hole, your trajectory would not be a simple radial plunge. You would be rolled by space-time, carried by geometry as much as by gravity. The darkness ahead would still be inevitable after the horizon, but the dance on the way in would be more complex, more baroque, more faithful to the real universe. Even in sleep, astronaut, it is worth remembering that the cosmos is rarely symmetric and still. It turns, it twists, it carries angular memory from dying stars into the black engines they leave behind. So, what have we truly learned from this fall? We have learned that a black hole is not a cosmic vacuum cleaner in the cartoon sense. It is a region of space-time shaped by mass. From far away, its gravity is no more magical than the gravity of a star of equal mass. You could orbit a black hole safely if you remained far enough out, just as planets orbit the sun. The danger is not the word black hole. The danger is getting too close. We have learned that the event horizon is a boundary of communication more than a physical wall. Crossing it may feel locally uneventful, while meaning everything for your connection to the outside world. We have learned that time is elastic under gravity, and that two honest observers can live through different stories of the same event. We have learned that tidal forces can unmake a body with the same family of physics that lifts Earth's oceans. We have learned that the singularity marks the edge of present knowledge, not necessarily the edge of nature. We have learned that black holes can die, slowly, through Hawking radiation, and that their death raises questions about information that still challenge the best minds on Earth. And we have learned that even the most terrifying places in the universe can be approached with calm attention. Fear makes the dark larger. Understanding makes it clearer. There is beauty here too. The glowing curve of an accretion disk, the Einstein ring of bent starlight, the patient mathematics that lets a species on a small planet predict the shadow of an object thousands of light years away. Beauty does not remove danger, but beauty and danger often share the same sky. The black hole does not hate you. It does not hunt you. It has no will, no appetite in the human sense, no voice. It is geometry under extreme conditions. It simply is. And yet, we give it stories because we are creatures who need meaning. We imagine falling in, not because we wish to die there, but because the fall is a way of asking what reality is made of. How does space bend? How does time flow? What remains when matter is crushed beyond every familiar form? What rules still hold when our oldest equations fail? This is the quiet courage of science, to look directly at the place where knowledge ends and to keep looking. You have done that tonight, astronaut. In the safety of rest, you traveled to a region where light is trapped, where clocks disagree, where the future narrows to a single direction. You did not go there with panic. You went there with attention. That matters. The universe is full of soft wonders, nebulae, quiet moons, gentle starlight. It is also full of severe wonders. To know only the gentle half is to know only half the cosmos. A sleeping mind can hold both. And so, our journey ends, or perhaps it only settles into memory. Tonight, we fell toward the darkest kind of object the universe can build. We watched starlight bend. We crossed a horizon that cannot be uncrossed. We felt time loosen from its ordinary pace. We faced spaghettification, singularity, evaporation, and the long silence of unanswered questions. Now we return, not by climbing out of the black hole, for that cannot be done. We return because this was a journey of the mind. The body remains here, safe, heavy, human, on a small world under a kind sky. The fall was real, only as understanding is real. The universe is vast, and we are small. But tonight, astronaut, you traveled far. You went to a place where light cannot escape, where time loses its common meaning, where the fabric of reality is pulled to its limit. And you came back with something worth keeping, a clearer sense of how strange and how ordered the cosmos can be. Rest now. Let the darkness around you be the gentle darkness of sleep, not the absolute dark of an event horizon. Let your breath move easily. Let the day dissolve. Tomorrow, the cosmos will still be there, with new secrets, new distances, new quiet miracles waiting for another night. Mission complete, astronaut. The stars will wait for you. Good night.